Okay, now we actually want to talk a little bit about one of the chiller plant efficiency. So today, this particular session is about aircon, and of course the air conditioning performance plant, right, which is the plant performance itself. So with that, the learning objective one is able to explain the instrumentation, how you look at instrument and you read the chiller plant in the air handling unit. The second is basically to be able to explain the chiller plant performance where you calculate the heat either efficiency and the heat balance. So there will be two methods that will be shown, right, and then we'll kind of show you a little bit later about the two methods. Yeah. Alright, and then the third one is basically you're able to calculate the pump efficiency. So with that, when you're reading the chiller performance data from the BMS, and this is what you can see that actually from the power meter, right, where there is power that you are able to see, right, and then from there you can see the different powers in the different ratings, three voltages, right. So with that you basically have the voltage and the currents, and then finally you have the power, which is here. Alright, so where you can see so for this particular course we will just only focus on the power. We will not talk about the balancing of the electrical power, but either way this is how it's be done in kilowatt, and then the energy which will then be calculated in kilowatt hour. So with that, that is the power meter. The other side you might want to look at is basically the chiller plant schematic. From the schematic you'll be able to see something called the heat balance. At the same time you're able to see basically the RT of the chiller itself. So that's how we actually can look at the chiller performance. So something you need to learn to read about this. So getting that, remember just now I talked about the readings of the power readings. So this is basically in kilowatt. Yeah, that is basically the power reading of it. And then once you kind of read, let's say the cooling tower, the condenser water pump, chill water plant plus the chiller, you add it up together, this will give you the system power, right. After which you can have a calculated power, kilowatt per RT. So you have, for example, the first one will be, right, will be 0.6 divided by 19 will give you approximately about 0.03 something. That is basically your kilowatt per RT. Yeah, right. And then you calculate that through, and then BMS efficiency is also being calculated. Then you will actually have something called a heat balance. This is the calculated versus the BMS part of it, and you will have or something of heat balance. So something along the line of 10% is still reasonable. More than 10 to about 15% usually it's like yellow, and then more than that 20% is kind of red in color. Why is it so? Because there's a certain drift in terms of the calculated versus what is being presented. Yeah, so that's something that you will need to learn how to read the chiller performance from a BMS system. The chill water cooling, the chill cooling capacity and performance, basically what we need to learn is a few things. One is Q equals to m dot mCp delta T, where Q is your heat, right, your heat exchange, where heat exchange is usually in kilowatt, and then your mass flow rate, or we can say mass or mass flow rate, is in kilogram per second. But sometimes you is also given liters, but usually we want to put it in kilograms per second, because mass is like mass, right? Mass is in kg, how heavy you are, to move from 1 kg of water in 1 second. Specific heat capacity of water is nothing much but the ability to heat up water in 1 kg per 1 Kelvin. 1 Kelvin in this particular case is also 1 degree C, right? So you will take about 4.19 kilojoules to heat up 1 kg of water in 1 Kelvin, in 1 degree C. So this tells you how much water in terms of your heating capacity. So the higher it is, the more heat capacity you will become, meaning to say you take more heat right, to actually heat up such certain thing. So in this case, maybe good or maybe bad depending on the application. If you want your water to heat up fast, you probably want a kind of higher heat capacity, so that you actually has more Q, right? Because your Q times your MCP, your higher heat capacity will give you a better Q. Higher Q means that you actually have more heat exchange. So with that, high and low temperature is very easy to explain. The higher or lower temperature, the difference of temperature is the higher temperature minus the lower temperature. So equation given is Q equals to your M Cp delta T. There's a missing M here, and the specific heat capacity is 4.19. So with that, we want to calculate the chiller performance. So by looking at the parameters, you can then collect different parameters here, right? So you just collect, and in terms of calculating, because we want to learn how to calculate, and this is basically the heat capacity equation. So with the heat capacity equation, you can then calculate one, the chill water capacity, which is your m dot Cp delta T, right? So you see this is 4 is from here, and then your Cp, which is a standard, right, is 4.19 unless we change to a different media, minus your delta T. In this case is 10.5 minus 6.5, which will give you a kilowatt in refrigeration done. So you divide this 67.04 in 3.517 will give you certain RT, in this case about 19 RT, right? So the second step is to talk about heat rejection. Heat rejection is from where? From your condenser water side. So from your condenser water side currently is running about 5, right? So something you might want to remember is your condenser water is much higher. With a higher water, right, their flow rate has to be more, so that what will happen? You will then able to reject heat. Reject heat in a way that in this case the heat rejection is much higher, correct, compared to your cooling capacity. So your electrical power input is calculated, where you can see the input is approximately about 23. This is, you get it from your meter. And then finally the chiller performance is your kilowatt divided by your RT. So your kilowatt is 23, your RT is how much? About 19. So this is 23 divided by 19 will give you approximately about 1.2, right, or 1.2 kilowatt per RT. Okay, so with that, something we shared just now, right, total heat is basically your cooling capacity, your chiller cooling capacity plus your electrical power input. So in this case, it's about 67.04 plus 23, right? Then it gives you about 90. So your total heat is approximately about 90, right? 90 kilowatt. So with that, you actually have what? You actually had your heat unbalance, meaning to say your total 90 minus away by your what? What is this? This is basically your chiller heat rejection, right? So your chiller heat rejection will give you about 81, and then minus this off this divided by 90.04, which is your total hot input. So your input minus away your heat rejection divided by your total heat, right, will give you something called your heat unbalance. That's where the 9.26% comes from, right? So with that, the last part we talk about is pump performance. So what is pump performance? Pump performance is basically knowing how much your pump is performing, and from there is 4 of them that you probably want to know. One is your pump flow rate, second is your pump pressure, pump power, and pump efficiency. So if you know all these few units, you are able to kind of calculate that through. So the first piece is basically your pump power is your pressure multiplied by your pump flow rate. A lot of time we call it m dot. Your pump flow rate, as mentioned, it could be meter cube per second. So so that's how it's been kind of been done. So usually 1 meter cube, right? Yeah, will give you approximately about 10,000 liters. Okay, so with that, the second piece is your pump efficiency, which is your output divided by input power, and sometimes it's a pump power divided by your electrical power. So with that, we are able to start right now. Pump pressure, which is your outlet discharge minus your inlet. So assuming this is your pump, something is on discharge, your pump will definitely discharge, right? Discharge pressure, which will give you approximately, in this case, right, about 1.12 bar. Your suction pressure, which is here, is usually very low. In this case, it's about 0.28 bar. 0.28 bar. All right. So with that, you get your pump discharge, pump suction, and then you have your chill water flow rate, which is 3.1 liters per second. You convert that into meter cube per second, which will get about 0.0031. Electrical power is calculated, yeah, and then finally your electrical output, right, will be your pressure times your volumetric flow rate. How you get this pressure is your out discharge pressure minus your input pressure, yeah. Okay, then finally you will get your pump electrical output power. So from the pump efficiency, basically you have your pump output electrical power divided by what? Your electrical input, which is the 700 watt, which will then give you approximately about 37%, yeah, of the efficiency. So with that, we come to the end of this session, and what you have learned is you're able to explain the instrument, take a look at the instrument, know how to read the chiller data, right, and basically how much air is going through. The second piece, you are able to explain the chiller performance, yeah, and calculate some efficiency, which is kilowatt per RT, right, and then your heat balance, which I kind of shared just now. Finally, you're able to learn about calculating the pump efficiency, which is your output divided by input multiplied by 100%. Yeah. So yeah, this is the sharing